great pleasure to introduce to you our keynote speaker of today, Professor Madhu Khanna from the University of Illinois. She is a professor of environmental economics in the Department of Agriculture and Consumer Economics and the Alvin H. Baum Family Chair and Director of the Institute for Sustainable Energy and Environment. She has done a lot of work on the sustainability, energy, and environment in her research. She received a PhD from the University of California at Berkeley under the guidance of David Silberman. Her research is at the intersection of agricultural, energy, and sorry, I cannot read this well, environmental economics, and includes analysis of land use and environmental effects of bioenergy, the potential for climate smart agriculture by co-locating agriculture and solar energy through agrivoltaics, and economic incentives for using artificial intelligence-based technology for sustainable farming. She has widely published more than 150 peer-reviewed publications. She has worked on the US EPA Science Advisory Board. She had been the president of the American Association of Agricultural Economists. Last week, she gave a keynote speech at the meeting of the European Association of Environmental and Resource Economists. So we are very happy to have you here. You have a very busy schedule. Madhu will talk today about feeding the bioeconomy, choice and consequences for climate change mitigation. Madhu, the floor is yours.
Thanks, Eustace. It's a pleasure to be here, and thank you for inviting me to share my work today. So my talk is going to focus on some of the choices we face as we think about moving towards a bioeconomy and how to assess its consequences for climate change mitigation. The recent sixth assessment report of the IPCC has noted that in order to keep to the 1.5 degrees centigrade limit, we have to not only reduce emissions, but actually have to adopt some negative emission pathways in order to get to net zero by 2050, and then be able to get to 1.5, keep that limit of 1.5 degrees centigrade. And there are various approaches for CO2 removal, called these carbon dioxide removal strategies from the atmosphere, and then sequestering this either in forests or in agricultural lands or other land uses is really the approach that is needed, and a significant amount of negative emissions are needed in order to stay within the target. And then the IPCC report also notes that there are a lot of uncertainties in how we're actually going to get to these negative emission strategies, and there are going to be many trade-offs and have economic and social implications and so on. And so I want to discuss a few of those today. So, and the strategy that, we talked yesterday about, the strategy, at least in the US, is along similar lines, really, in terms of moving towards this as a way to mitigate climate change, and to do that through, producing, the goal is to be able to produce 1.2 billion metric tons of biomass. Previously, this was by 2030, now being obviously extended, but at least technically there is a potential to produce that. And if we could do that, we'd be able to replace a lot of fossil-based energy for bioproducts, bioenergy, and so on. Sustainable aviation fuel is growing in importance, and the goal is to really have low carbon sustainable aviation fuel, which requires going beyond existing feedstocks to new feedstocks that are low carbon. Developing large-scale solutions for soil carbon sequestration and being able to quantify and measure and incentivize that is another goal, along with using biomass, carbon removal through geological sequestration as well. So So there are several things that we need to consider as we think about how we would achieve these goals, both at the global level, at the national level. And there are many choices of biological feedstocks that could be used in order to move towards this bio-based economy, including food crops that we're currently familiar and producing, crop and forest residues. We can have dedicated energy crops, agroforestry, forest biomass. And the challenge is that these feedstocks are very diverse in terms of their attributes, their potential biomass yield you can get per unit of land, the carbon intensity of these different types of fuels, the cost of producing them relative to fossil fuels and relative to each other. And not only different among each other, but there's a lot of spatial heterogeneity in how these attributes vary across. Question about which feedstocks should be produced and where should they be produced, what is economically viable, and how do we incentivize them. Forest and crop residues are very appealing because they are currently not being used. They're really being wasted in some ways, and therefore can be easily, or at least potentially, be used without diverting new cropland to producing feedstocks. But there's lots of questions that come up in terms of how much can you actually sustainably and economically harvest. Forest is another source that, of existing source of biomass, but many questions about whether we should be using forest as a sink for carbon or whether we should be using this as a source for biomass. And then there's the question, if we have to produce these feedstocks, where is the land, and what are the trade-offs involved in converting land from existing uses to biomass feedstock production? What are some of the unintended consequences of trying to produce more biomass? And then what policies should we actually be adopting in order to incentivize production? So, all right. And then, we cannot rely upon the market alone to move us and transition to this bio-based economy. We have to develop new supply chains, which don't really exist at large scale, almost anywhere in the world, to really produce this level of biomass. This includes, creating mechanisms for production, transportation, storage, delivery, and all of that. There's a lot of uncertainty of the long-term demand for biomass, and whether before investment can take place requires long-term contracts, decisions about what type of contracts those should be, whether it's going to be a vertically integrated industry, it's going to be contract farming, and so on. Is a huge chicken and egg problem, because establishment of these perennial energy crops and so on really require investment. There are establishment lags before you can get the biomass to be used. And then the market system doesn't really, has not been consistent in terms of making it profitable to switch from fossils to energy, to bioenergy. The price of oil fluctuates so much, as not had consistent long run sort of high prices that would create confidence that there will be this long-term demand for bioenergy. And then coupled with all that is the continued negative public perception that that focuses a lot on the unintended impacts, and therefore also creates barriers for this policy making in order to move towards this in a consistent way. So clearly there is a need for policy incentives in order to support the bio-based economy. And we're talking about high costs currently of producing feedstocks and using that for bioenergy and biochemicals that are much more expensive than fossil-based sources. Converting land, will require giving up land from existing uses, which is much more profitable. So the huge opportunity costs for farmers, there are high upfront costs for farmers and the industry, and a lot of risks associated with that. So these policies are needed at all ends. They're needed in order to induce landowners to convert land from existing uses to biomass production, and as well as consumers to be willing to pay more for bio-based products as that is more expensive, and so on. And then it requires investments in infrastructure, as well as in equipment. You know, if we have to go to higher blends of biofuels, we need flex fuel vehicles, new market institutions, and so on. And here too, there's a choice of many different policies. Technology mandates and tax credits have been the most commonly used across the world. Rather than performance-based policies that are really focused on the carbon intensity and would encourage the production of feedstocks that are less carbon intensive than others. Major concerns really surrounding this have been these concerns about the unintended consequences. And there are numerous ones there that one could focus on, and a lot of trade-offs that have to be considered. And so in the case of using food crops or using dedicated energy crops, ultimately going to compete for land one way or the other with food production. And we can talk about which ones are more, the trade-offs are more intense than with others. But either way, they're going to require land. And that could be either cropland or it could be non-crop land, which also poses its own challenges. So when we talk about a bio-based economy, there's a lot of concern about negative impacts on biodiversity. For example, when we switch from native grasslands to monocultures, for example, of energy crops. To varying degrees, these biomass feedstocks require inputs, and nitrogen fertilizer, they could be grown under irrigated conditions, although one would hope not. But there's a potential with nitrogen fertilizer use of nitrous oxide emissions, nitrate runoff, and effects on water quality. In the case of forest biomass, especially if we're talking about medium to long run rotation forests, converting those to biomass involves payback periods, and I'll also talk about that in a little bit. And also, there's lots of questions about how should we account for the carbon savings or carbon emissions associated with harvesting trees for bioenergy. There's questions about choice of baseline, the time horizon that is used for assessing carbon impacts, and the type of forests that get converted. With crop and forest residues, they also serve an ecological function when they are left on the ground, and only a portion of that should actually be removed in order to prevent negative impacts on soil quality and erosion and so on. And so these, with all of these feedstocks, to varying degrees, there are issues of the potential for a carbon debt being created before we can actually get the carbon savings. And there's typically going to be a payback period, and that'll vary in length, but there's this a concern about the fact that there may be short-run spikes in emissions before we can have the savings, and are we willing to accept those in order for the long-term benefits? So, just in terms of current status, this is where we are. Major use of food crops for producing bioenergy across the world. The maps on the right show the mandates for blending in different countries. And the major producers of ethanol have been the US and Brazil from corn and sugarcane. The EU is the largest producer of biodiesel, and there are many countries that have mandates and are increasing production, with goals of sort of increasing the blending. But going beyond these sort of, first generation feedstocks, food crops, there is a whole potential for using perennial grasses. These are high yielding grasses that have been demonstrated to be grown very productively without as much inputs as needed for food crops, and the ability to provide just a variety of additional ecosystem benefits, high carbon sequestration, much more than corn and soybeans. They can be grown on less productive land, and very high conversion efficiencies. And the use of this biomass avoids the need for fossil fuels to convert it into bioenergy and bioproducts. And so they have the potential to really produce negative carbon intensity products compared to their fossil alternatives. And to be able to also provide other benefits like low nutrient leaching and improving soil health, soil fertility, and so on. And so there's been a lot of work looking at that and being able to, both experimental research that demonstrates this now over the last, several decades that this has been going on, as well as models that have been then built on this data to extrapolate it to larger regions and to be able to show conditions under which these types of grasses can be grown, and then what their overall benefits and so on are. And so this is just sort of an example of some of the work that we've been doing, looking at the rain-fed regions and looking at the potential to grow these types of feedstocks, looking at 4 in particular here, miscanthus, switchgrass, there's energy sorghum, and then comparing that to corn stover. And so this is, growing them under rain-fed conditions, and their, input requirements relatively lower than that of corn, but they vary. And, but you could sort of see here, there's a lot of heterogeneity, especially in terms of where the yields would be more than compared to others, comparing across feedstocks. And certainly the yields are several times larger than what one gets from the crop residues. There's also huge potential for carbon sequestration, and in some, it varies across locations, but clearly there's much more than the use of corn stover, which even with low rates of harvesting, 30% or up to 50%, actually results in a loss of soil carbon. Looking at costs, you can, translate the yields, translate very much into areas of cost where the costs are, so costs are low and yields are high. And those, now if you compare costs, we would see that corn stover is really is much less costly than any of these other feedstocks. And but then also it has much higher carbon intensity compared to the others. So the other feedstocks, all in blue, have got negative carbon intensity compared to gasoline, whereas corn stover is less than gasoline but has a positive carbon intensity. So a lot of choices there in terms of which feedstock should be produced and where you would want to produce it and where it might be economically viable to do so. So if you look at abatement costs, we can sort of start to see the challenge of why it's not being readily produced, and that is the high cost of abatement with any of these. Even if we're looking at these high yielding perennials, the costs of abatement are at the lowest end are still about $150 to $200 per ton, vary a lot across regions and so on, and significantly higher than any estimate of the social cost of carbon that we might currently be using. So, it poses this question of like, what is the optimal choice, and depends upon very much what goals we might set for how to choose. If we have the goal that we want to use the minimum amount of land and have the highest yielding energy crops and feedstocks, then we would get a particular mix. And this shows the particular feedstock that achieves that goal the best. And so you could see large areas where miscanthus would be the preferred feedstock, and followed by energy sorghum. If we were looking at the lowest greenhouse gas intensity, then switchgrass would be the preferred feedstock. If you're looking at the lowest greenhouse gas abatement, you get a different configuration. And each of these configurations is possible depends very much on the policy that is in place. So mandates, for example, incentivize the lowest cost way of meeting the mandate, and the lowest cost way, rather, because it has no carbon benefit, and so that is being rewarded. And so we get the mix that shows the lowest ethanol cost, that is in the second map there. If you had a carbon intensity standard that rewarded different types of energy based on the greenhouse gas abatement, you'd get a different mix of feedstock. So policy would really translate into which types of feedstocks are produced and where they are actually produced. So the question of where to produce these feedstocks and how much land do we have, which type of land would actually be used, and is that, what are the consequences of that? And so we can look at, these types of crops can be grown on low quality marginal land, and the challenge is defining marginal land. There's numerous definitions of marginal land in the literature. As economists, we would like to define this as land that has got low profitability, that is at the margin of crop production and non-crop production, that is earning close to a zero return. And so that's the area to the right of that dashed line where crop production is not profitable. Now, if we look at what happens when we add in this bioenergy crops to this mix, we can see that bioenergy crops would have lower, would have higher profits on low quality land. And so they would extend, part of that would be grown then on this marginal land. But depending upon the biomass prices, depending upon crop prices, the intersection of the blue line and the yellow line will determine how much of cropland may also get converted to energy crops. And so energy crops are going to be grown not just on marginal land, they're going to be grown partly on cropland and partly on marginal land. And the challenge is that both ways they are in trouble in some ways, because if we grow them on non-crop land, then that raises concern about the potential to convert native grasslands to energy crops, and then loss of ecosystem services, biodiversity, and so on. If we grow them on cropland, then that has a potential to raise food prices, and that also can lead to a cropland expansion and indirect land use change, and have its own greenhouse gas implications. So either way, energy crops, there is concern about producing these energy crops, and the question is, which land would be better? How would, where does the carbon debt going to be greater, and so on. So it becomes a more complicated question of actually trying to figure out, which land is likely to be converted, and what is its carbon stocks, and what gets lost, and how much will be made up by carbon sequestration, and so on. And coupled with that is the challenge of actually quantifying the amount of marginal land that exists using, we don't actually have fine resolution data on the returns to different types of land. And so here in this study, we actually use satellite data and a history of satellite data of land use change over time from the cropland data layer. We can look at which type of, how much of land is actually marginal, how much is grasslands, and so on. And there's a lot of uncertainty in quantifying land as being marginal. And but nevertheless, our best estimates are sort of reflected there. There's not a whole lot of marginal land really with confidence that we can identify in the rain-fed region of the US. There is quite a bit of land that is uncertain. And then there's quite a bit of grasslands, particularly in the Great Plains region, that could potentially be used for energy crops because it's rain-fed. So we use an economic model that integrates, the different sectors, as well as the some biophysical models and refinery scale models and so on, to really understand what would be the incentives at different biomass prices for producing a mix of feedstocks in this rain-fed region, and which land would it be produced on, what would be its carbon savings, and carbon costs, and so on. So, so this sort of shows that, as we allow more land to get converted, if we restrict production only to the marginal land with confidence, then we get much less biomass at given biomass prices. As we allow for more land to get converted, we move to the right-hand side of these graphs. You can see that we could produce 1 billion tons of biomass at high biomass prices, and that this would be produced from a variety of different types of feedstocks in different parts of the region. So there is a lot of potential economically to be able to do that. We can also look at what type of land it would be produced on, and it would be a mix of land. It's not just marginal land or cropland. It's going to be a different, mix of different types of land. Some amount would be produced on cropland, but then as we allow more non-crop land to get converted, then we can actually, we can see that some amount of grasslands and marginal land or idle fallow cropland, would get converted to produce these crops. So what is the consequence of doing that, and how much carbon is actually lost when we convert these non-crop lands? And not only do we have to look at what is the carbon loss due to conversion of non-crop land, but it actually has to meet even a higher standard. We have to really look at what would the carbon savings on this land have been, or the carbon sequestration on that converted land have been if it had remained in its current use. And so you have to look at that, what are the foregone opportunities and the carbon cost of converting that land. And so at different, with these different scenarios, we can see that there is a dip in the soil carbon stocks in the first few years. That carbon debt gets created. The carbon debt is greater if we allow grasslands to get converted. And then the dashed lines show that the foregone opportunities are keeping the grassland and maintaining it as is and letting it sequester carbon over time. So keeping all of that into account, we can see that it could take a few years for the soil carbon stocks to really catch up to what they would be if you were to leave the land as it is. But once you take into account the fact that you can use this biomass to displace fossil fuels, so we're not just growing them for sequestering carbon, but also for displacing fossil fuels, then you see the savings which are shown on the bottom panel. And then the carbon debt is actually non-existent, and the displacement effect is so large that it can more than make up for that carbon debt, and you get significant savings in emissions. So what would that translate? How much land is actually needed then to get the carbon savings, at different biomass prices? And you could sort of see from here, the top panel shows the amount of land that is needed, the percentage of total land that is converted, and the percentage of savings we can get by displacing fossil fuels in transportation. This is just focusing on displacing, transport fuel at those different prices and with that land conversion. So you could, for example, you can get a 20% reduction in transport sector fuel, greenhouse gas emissions by converting 6% of the land. And that could be grasslands if you allow that to happen, or it would have to be cropland. And then the price at which you can get that would also differ depending on cropland is much more expensive to convert compared to grassland. So you could see the trade-offs involved here in trying to get these greenhouse savings using land use change. The other issue that we have to think of is, will farmers produce these crops? Even if we, as policymakers and scientists would like to see this happen, what would it actually take for farmers to produce this? And there've been, we've done some work surveying farmers and modeling what happens when there are farmers that don't just care about profits, but also concerned about risk and they have, and so on. And the challenges with moving from an annual cropping system to a perennial cropping system is that it poses its own risks, and there are lags between planting and harvesting that require foregone income. There is high costs of establishment. There's often challenges in getting credit. And so it really poses a big negative impact in the short run for farmer income, requires very long-term commitments that are typically not the case with annual crops. Require giving up current income. And then there are risk preferences and time preferences that will play a role. So farmers surveys, and our own work indicates that tend to have very high discount rates. And so they really require very high returns to be willing to invest today and wait 10 to 15 years to get that return. Other issues relate to the fact that, at least in the US, there is just such an increase in absentee landlord that so the decision making is not really being done by the farmers that are operating the farm, and so that makes it much more harder to get changes. The age of farmers in the US is getting to be about 60 years on average, and so there's a reluctance to really invest in things that require long-term commitments. And so there's a number of challenges there that would need to be overcome. We look at, for example, just two or three factors such as risk aversion, time preferences, credit constraints, and we can immediately sort of see that supply curve for biomass begins to shift to the left There's a preference from, say, miscanthus, which is high yielding, but also has long establishment periods and costs, to switchgrass, which is less high yielding, but is an immediate return. And so it begins to change the amount that can be produced at different prices, and really will raise the cost of feedstock production, at least in the US. Looking at forest biomass, that poses a number of challenges as well. And this, although on the surface, it appears to be, it might appear to be a sort of no-brainer to think about forest biomass as being preferred to fossil, energy from coal, for example, because it's really just recycling carbon. It is growing, taking carbon out of the atmosphere, and then putting that in the plant and then into the tree, and then you harvest the tree, and it's going to sequester more carbon, and should be preferred to coal, which is a unidirectional emissions that are going to be permanently in the atmosphere. But it turns out to be an extremely complex question that depends upon the time scale that we're going to use in order to compare coal with forest biomass, the spatial framework we're going to use to assess the carbon stock changes, what baseline is used, and then what type of forests are going to be converted. So just to dig into that a little bit, the challenge with using forests for biomass is that, if we look at just a stand of forests, when you cut down a stand of forests and use it for energy, it's going to take decades for that stand to get rebuilt again and to sequester the carbon. And so the immediate impact of cutting down a stand of trees and combusting it is going to be a carbon debt. We're going to have an increase in emissions in the atmosphere. It's going to take decades for that to come back to its original level, and then it can give some savings. And so there is this concern that you're going to first have a carbon debt, and then you have to have a payback period that could be several decades. And that, is that payback period really acceptable? Is the fact that it could take 20 to 40, 50 years before that we come back to where we were and then start getting the savings, is that an acceptable payback period from a climate impact perspective? Now, that's one way of looking at the impact of forest biomass harvesting. The other approach is to not do the accounting at the stand level, but to do the accounting at a landscape level. And so commercial forests have to continually be harvesting and growing trees, planting and harvesting, to provide a continuous supply of forest biomass. So when you have pulpwood and timber and so on, we're not waiting 20 years for the trees to grow back before we get the next stock. These forests are really managed at a landscape level, and some part of the forest is being harvested, other parts of the forest are being planted, and there's a continuous supply of biomass that is being generated every year in order to keep the forest industry and the forest product industry operational. And so if we use a landscape-based approach, then really in an equilibrium situation, the carbon stock in the forest could be considered to be in equilibrium. We're not seeing dips and rises. There is, as I said, there is continuous growth and harvesting and planting going on. And so studies which use this landscape-based approach to carbon accounting actually find that forest biomass can be considered carbon neutral, because it's growing and it's harvesting and sequestering at the same time. Now, of course, all of this still doesn't consider economics in it. If we add economics to this and we take a dynamic view, then a demand for bioenergy is not just going to lead to a cutting down of trees and replanting. It can lead to multiple changes. It can lead to cutting down trees earlier than you would otherwise, increasing the intensity of forest management, changing the amount of land in forests versus in other things, and so on. And could even lead to anticipatory planting, where in anticipation of biomass demand, more land is converted to forests. So there's multiple things that could happen that make this, really something that one has to, that is hard to sort of say offhand, and you have to do a pretty extensive modeling exercise to figure out really what is the impact of that on carbon. Another question is what baseline to use. And so you could think about we have to compare, we know as economists, we will need to compare, keeping everything else the same, what happens with bioenergy or feedstock production and without, and so the typical, the easier thing to do is to say, well, what is a carbon stock today, which is the reference point, and then what is a carbon stock with bioenergy? So you compare point A and point C. And of course, that is not the right answer. We really want to be comparing point B to point C. What would have happened without bioenergy and what would have happened with bioenergy? So if we compare point A and point C in this particular thing, we would say, it should be considered carbon neutral because the carbon stock is actually growing, even though we have bioenergy. If we compare point B to point C, then we would say, well, no, the carbon stock is actually lower than what it might have been if we had not used forest bioenergy. And so that to compare point B to C, you have to develop a counterfactual baseline, which is not easy to do. It is not an observed baseline. It's a counterfactual that has to be created. And in order to do that, and a lot of uncertainties associated with that. So depending on the baseline, we can get very different answers for what the impact is. The third major controversy is really about the time horizon. So this particular graph shows this, the black solid line shows what happens when you use fossil energy. Carbon emissions go up, and they're pretty much going to be in the atmosphere for a very, very long time. In the case of bioenergy, depends upon from forests, it depends upon the rotation. If you're using short rotation, quickly growing feedstocks, then there is an initial spike. There could be an initial spike because of a carbon debt, but then rapidly the trees grow back or the energy crops, sequester carbon, and we get a saving compared to the fossil energy line. If we use long-term long rotation trees, then we could have a bigger spike. It could take a little longer, but ultimately it's gonna be better than fossil energy. But the question is in the near term, in the next 20, 30, 50 years, before we actually see that dip in the atmospheric carbon, is that going to lead to a tipping point? And so there's a lot of uncertainty about how long it takes carbon emissions in the atmosphere before they're really going to change global temperatures. And that's something that there's not a whole lot of scientific resolution on. According to one view, you need to have the carbon emissions need to be there in the atmosphere for at least 100 years, cumulative emissions, in order to affect global temperature. But then there are others that would argue that in the short run, you could actually worsen the impact and through these tipping points. So there's scientific uncertainty, and there isn't a clear answer. So there's just a number of challenges with implementing these types of carbon dioxide reduction strategies. A major part is, if we're looking at soil carbon, is measurement, monitoring, verification, which is costly and uncertain. As I said, the choice of baseline, the choice of additionality, what is the additional benefit you get from switching to carbon sequestering practices compared to anyways? Establishing that counterfactual of what would happen anyway is challenging. The choice of time horizon for assessing impacts. The fact that carbon in soil, vegetation, trees is ultimately reversible, and it's impermanent and not the same as permanently keeping fossil fuels in the ground. There's leakage due to land use change. We have a number of carbon credit programs that are existing, but the transaction costs of participating in them and the credibility of many of those carbon credit programs is sometimes questionable. Current policies in the US actually don't reward farmers for soil carbon sequestration. It's just not being explicitly done. And then there's concerns about greenwashing because we don't know, because of all the measurement, monitoring, and additionality concerns. Other complexities about these types of policies is that, as I said, mandates are really prevalent across the world. But they would incentivize the lowest cost feedstock and also production in the lowest cost regions. and not necessarily the ones that are the lowest carbon, but maybe more expensive. And so they can also actually, for example, in the US, they would incentivize corn stover, and that's really been the experience. The previous biofuel refineries that did come up using second generation fuels were all based on corn stover for exactly this reason. And too much of harvesting of corn stover, if the biomass price is high, can actually worsen nutrient loss, can worsen water quality, and have its own negative implications. So we need to not only have biofuel or bio product mandates, but we need to have supplementary policies that can prevent these negative impacts on multiple ecosystem services that are impacted when we convert land from one use to another. The other is, of course, trying to have carbon intensity standards. And we have, for example, the low carbon fuel standard, but which would incentivize feedstocks with the lowest cost of carbon abatement. But with those, you cannot really guarantee that emissions will actually go down. So you could have intensity go down, but emissions may go up because of other perverse effects in the fuel market. Carbon taxes would be our preferred choice, and a global carbon tax would be the ideal way to go, but of course would have to be very high, politically very difficult to do. For farmers, these policies actually may themselves not be enough because they don't deal with risk. And so in order to reduce risk of producing these energy crops, we need to have establishment cost share subsidies to cover the upfront costs. There's no crop insurance currently for producing these new crops. Low interest credit is needed. And so really the idea is that you have to have multiple policies that are simultaneously put in place to encourage that entire supply chain to develop and to achieve these various goals and prevent unintended impacts. And these have to be long-term and credible commitments that have to be there. So to conclude, there's a lot of potential for producing biomass from high-yielding perennials, short rotation crops or trees, grow them on marginal land, of which there certainly is some, varies across countries. And these have the potential to provide the negative carbon intensity feedstocks that are really required in order to get to those net zero goals. But we need policies that would induce production of the feedstocks that are indeed low carbon intensive, and that can avoid conversion of the carbon-rich grasslands or lead to deforestation and those which could be problematic. And then recognizing that there is likelihood of having these short-term carbon debt due to land use change, but then to have the patience to wait for the long-term carbon savings. And there's a lot of uncertainty about the acceptable payback period. And, is a 100-year payback period, should we take a 100-year horizon or should we take shorter horizons as we try to assess the impacts on climate? And ultimately, this is sort of an issue that because there's scientific uncertainty, ultimately comes down to policymakers. And policymakers policy horizons are much shorter. So current policy horizons are, have been sort of in the 2030 range for a lot of policies. And it's unclear what the commitment would be longer term. And so if we invest or use these long-term, use feedstocks with long-term payback periods, then there is no binding mechanism to make sure that we will actually get that payback and will actually happen, after the current policy cycle. So those are some of the challenges as we think about, moving towards these bio-based feedstocks. And we'll stop with that and happy to take questions.
Madhu, many thanks for an excellent talk and with some dismal conclusions to be drawn, like taxes that we would need to achieve what we would like to have from a climate change perspective too high, that society would not be willing to pay for that. And then other strategies that may hide a little bit those costs may not achieve what we would love to have. So we're cheating a little bit on ourselves. That is something that I get out of your presentation. And it's nice to see, to get this demonstrated, what is really happening, what are the trade-offs that you are facing. And I think you did an excellent job showing this to us. What are the challenges for having something that is able to achieve what we want, politically sensible and societal acceptable by society. But now I'd like to open the floor for questions and comments. Carl.
Thanks, Madhu, for a very nice presentation. I was, excuse me, wondering, to what extent the cellulosic or lignocellulosic process is really, getting down in price, and is that likely to go down in price? And then how does that affect your calculations, or have you already incorporated that in some sense?
Yeah, so the whole lignocellulosic production and conversion of cellulose to producing fuels there's a lot of research that's been going on, and it seems to be a fairly intractable problem. And even though scientists know how to produce this in the lab, but scaling up to be able to do this in a continuous refinery process is actually a bigger challenge than has been really than anticipated. And a lot of research is, for example, in my center has shifted attention away from grappling with this problem of how to convert cellulose to fuel, to actually thinking about how we can change the plant itself and engineer new plants that can produce oils that could be more easily extracted as compared to converting the cellulose into sugars and then into fuel. And so there's research is now looking at how we can, for example, convert, the sugarcane family, energy cane, into oil to produce oil, or sorghum to produce oil, which is, again, it's a very long-term research agenda. They're able to produce small percentage of oil, but it's may work in the long run, but it's not there currently. So.
David?
Oh, this was a really fantastic talk, and we need much more research along this line. Unfortunately, economists love the past, and Madhu is one of the rare people that really look at the future. But the one thing that I'm really interested in, you start speaking about it, that almost all the people that work on biofuel behave as if biotech doesn't exist. And to some extent, one of the main advantages that you can have if you have a better regulation is that you can increase yield of existing feedstocks. If you look what happened to the yield of corn with GMOs, and if you start looking at what can happen with sugarcane or other things, I think it can alleviate a lot of the problems. So to some extent, there is any information to get to predict how biotechnology can affect it? Did you try to introduce it to the model?
So two responses to that. I mean, one is that, one could argue that biotech is that biotech going to happen anyway? And you're going to see that increase in yield because of things that are not related to biofuel. There's improvements in crop varieties that are taking place for their own reason. And then you have this problem of climate change. Is it really going to be a net increase? It's just going to keep up with climate change. So there's that issue, which can kind of, be the offset to what you're saying. But the relevant, issue is, is biofuel production and the price increases induced by biofuels, are they going to lead to larger increases in crop yields than you would have seen otherwise. And then it becomes, and that has been considered. And so in fact, a lot of the more recent models, including like the GTAP model and others, are taking into account this issue that increase in crop prices affects crop yields. And so that, does offset the negative impact. And so the earlier models which ignored that were getting this huge land use effect like Searchinger and others, and the more recent papers, which include that crop price elasticity of yield, find a much more positive impact. But one could argue, how big is it? What's going to happen with climate change? So there's lots of uncertainties there. So.
Thanks for this amazing presentation. I wonder if the emergence of electric cars can affect the fact that you mentioned that all of these things are long-term, need some commitment with the long-term action.
So electric cars are certainly, catch people's imagination much more, and they seem to be almost one that avoids a lot of these issues because you don't need land. You can use solar energy and wind energy and push to renewables and have zero emission vehicles and so on. There's sort of two counterpoints to that. One, that as we start looking at solar energy, that too is actually going to require land, not at maybe the same magnitude as bioenergy, but utility scale solar, which is the largest growing solar across the world, or certainly in the US, is quite land intensive. And a lot of the land that's getting converted is cropland. In Illinois, it's actually more profitable to do solar farming than crop farming. So it doesn't fully offset the land food versus fuel issue. But the bigger challenge is that electric vehicles are very expensive, and they're not and they're likely to remain more expensive than conventional, at least till the 2050 time horizon, even with reductions and optimistic assumptions about battery range increasing and so on. So very large government subsidies are currently needed in order to incentivize the increase in electric vehicle adoption. And if you look at these, in fact, the talk that I'd given at the European meeting was on that, and looking at the amount of savings you'll get in greenhouse gas emissions over a 10-year period compared to the cost of achieving that is very high, and almost at a similar level as with bioenergy. So yes, we could do that, and maybe with less land conversion than with bioenergy, but there's a limited potential. Because trying to get to the current target is to get 50% new sales by 2030 in the US. To get to that 50% sales, the amount of subsidies that are going to be needed is huge. And the savings you'll get is not proportional. So,
thank you.
Hi. Thank you very much for your presentation. The conclusion is very relevant. In this context, I have two questions. What is the role of the communities, and what government mechanics is we recreate on this new scenario?
sorry, could you repeat that question?
What is the role of the communities and the governance?
Yeah.
Thank you.
So I think, significant role for the government, with all of without government incentives, without government commitment to this policy, nothing would change. That is for sure. A role for communities, I think that there's actually apart from the government, there is a significant role for community, and that is in changing the beliefs and perceptions. And so just for example, and those beliefs and perceptions are not always economically driven. They're often driven by other desires. And so the agricultural community, and just speaking from the US perspective, in general tends to be fairly conservative and with a desire to preserve existing lifestyles, and they don't like to see a change in the landscape, and so there's a lot of opposition to new crops to putting up solar panels, to seeing wind energy go up. And so all of those kind of, the aesthetics make a big change and a difference. And so having community, greater community awareness of what are some of the benefits and so on, I think is really important. Having community leaders who can influence and, educate, and role for extension and so on is certainly there. Because that's the big hurdle is really getting people to accept and adopt new ways of life and things. So.
Thank you again, Madhu, for the fantastic overview. I enjoyed it a lot. I wanted to ask you about the biological carbon capture technologies. There is a huge hype around them now and huge investments going to the industry, but also many uncertainties about their these technologies. What do you think are their prospects? What are their potential? Will it be actually exhausted, or we need to go back and focus on the standards mitigation?
So yes, a lot of hype, and even beyond the bio sector, even with the conventional crops, there is a lot of interest in, for example, in cover cropping and no tillage with conventional cropping systems. And so even though, on a per acre basis, the amount of carbon sequestration you get is relatively modest. But if you look at the millions of acres that are undercurrent crops, and if they were all to convert into doing cover cropping and no-till, you could get a pretty substantial amount of carbon sequestration. But despite the hype, the adoption rates by farmers are very small. And the US, for example, with cover cropping, only 10% of the farmers are doing it, even though there are carbon credit markets and payments for carbon, government subsidies being given, and so on. So there's a number of hidden barriers that need to be overcome even there, which seems to be, well, a low risk kind of additional income beyond what you get. But there are hidden risks associated with that, which and upfront costs and so on. And again, the major issues are, proving that this is in fact additional. Farmers wouldn't have done it anyway. There's the impermanence challenge, the potential for leakage, that they may be doing it in one place and not. So those fundamental challenges continue to remain. I think the biggest challenge is really being able to monitor and measure at scale. The current technology of being able to measure using soil cores is expensive and can only be done, so often. And so there's a lot of credibility issue of really how much our carbon sequestration are we getting.
Yeah, thank you for a fascinating presentation. You pointed to this problem that the energy crops either grown on cropland or they're grown on natural vegetation, and then you have loss of ecosystem services. What do you think about the strategy to invest into other kinds of energy crops that may at the same time have biodiversity benefits because they are flowering plants and so on? So they may have a somewhat lower energy output, but at least they reduce the biodiversity trade-offs.
There is a potential to do those types of native prairie grasses that would be the native grasses, provide those ecosystem services. The big challenge there is that they're very low yielding. So compared to these energy crops, which give you about 20 tons of biomass per hectare per year, with the native prairie grasses, you might get 2 to 3 tons of biomass per hectare per year. So again, unless those ecosystem services like, pollinators or other, biodiversity impacts are priced to compensate the industry for using those grasses as opposed to the high yielding ones, from an industrial perspective, it would be very difficult to justify not planting dedicated energy crops. And then in addition to the yield, the other issue is that you have to transport this biomass. And so that requires the 2 tons per hectare, you need almost 10 times the land area on which to grow them, and then you have to transport long distances, which is a large part of the cost of biomass production. So, so that's part of the issue with using these native prairies.